So, we have looked at a number of different snippets of the code corresponding to the smart timer AXI interface. Now, I actually want to walk through the overall interface just to show you what the entire code end to end looks like, right, before we start running the simulation. And what we have over here is a brief description, right. This is generally good practice. Make sure that your comments and your documentation are not just in separate files, but are also included in the source code of the module itself, right. The module is written in a parameterized manner. You can see that I have given the address width as 6 over here. 4 was sufficient, right, because we are only using 4 registers. 6 is not a problem, but then effectively by giving 6, what it means is that you have to specify in the address map of wherever you are connecting it. Let us say you are connecting it to an ARM processor, you need to specify that it actually corresponds to 2 to the power of 6 locations, right, that are going to be there as addresses for this. In our case, we actually decided that because of the 0x00, this kind of address corresponds more to a 8-bit address if we just look at it, or we could consider it as 6 bits, which says that currently we have 4 registers, maybe I could expand it up to 16 registers in total, right. I have left that as potential expansion space. So, the address width that you specify over here is what is going to determine the maximum address that will be considered as part of this peripheral. The clock, reset and so on are inputs. All of these signals should hopefully look familiar. They are the exact same signals that were there in the register bank module. So, I am not going to talk about them in any detail here. The only extra signal that we have is, this is primarily for observation, right. It is an observable pulse width modulation output. Once again, you will find that a lot of the AXI Lite, the standard plumbing as they call, right. Why is it called plumbing? Because it is a matter of several different tubes that need to be connected up appropriately, right. Tubes or wires, you could think of it as an electrical network or a water network, but that is just a sort of casual way of describing it, right. This is not literally plumbing, of course. You have a bunch of registers which are used for all of these connections. Once again, the AW ready, W ready, AR ready, we discussed this in the context of the register bank and we know how the values are set. The handshaking happens exactly the same way, right. The AW handshake and the write data handshake, both of them happen out here. Now, where things get interesting is primarily in the actual update of the registers and logic. As you can see, now some new signals start to come in. There is a control enable signal, a control reset pulse, several registers out here, the shadow and the active registers for period as well as duty cycle. Also one register to indicate the update, pending updates, and another register which is the sticky flag, which gets set whenever the pulse width modulator output wraps around, or rather the pulse width modulator count wraps around. Default values for reset, right, rather than always prefer to use some kind of a parameter, a local parameter or a constant or a define or something. Local parameters are actually a good way of doing it because it allows you to specify the number of bits and all exactly. The idea is that if at all I want to change the reset value of the period, I change it in one place, and it is also more descriptive, it makes the code easier to understand. Now, let us look at the actual side effects. What do I mean by side effects? These are all the things that happen when you write to the registers, and similarly something else when you read back, but primarily we are going to focus on writing to the registers. So, this in other words, in the case of the register bank was very simple. All that we said was, depending on the address, take the data and store it in the corresponding register, right. Here things are a bit more complicated. Of course, we have a reset condition and we have a few if conditions or rather assignments out here at the beginning of the always block, right. Now, you might be wondering, why does it matter that it is the beginning of the always block or at the end of the always block? Isn't hardware supposed to be concurrent and everything occurring at the same time? Well, that is because of the way Verilog modeling works. In Verilog modeling, each always block, each assignment statement is considered to be concurrently operating, meaning that if I have two always blocks, I cannot be sure of the order in which the two always blocks are evaluated. But within an always block, the implication is that whatever functionality is desired is going from top to bottom. Why does that matter? Because it means that if I, for example, have a control reset pulse equal to 0 out here, and later I have an if condition that says control reset pulse equal to 1, that would take precedence because of the order in which it's evaluated, and the synthesis has to sort of account for that. If there is an if condition, then that is the one that has to take precedence and actually get evaluated. Now, as you can see, right, we already discussed this, a control reset pulse by default is set to 0. There is going to be another condition later where it gets set to 1. Where is that? That is if I am trying to write into register number 0, which corresponds to the control, and as you can see within that control register only 2 of the bits are writable. How do I decide that? I basically look at the W data Q of 0 and Q of 1, right. W data Q, by the way, has already been stored into a register as part of the data handshake. I look at those values and I say if I am actually trying to write into the lower order byte, then take this value Q0 and put it into the control enable, take value Q1 and put it into the control reset pulse. So, this is great. If I am actually writing into a location, the address will be here. I will have the do write signal, which basically gets set depending on whether the handshake, when the handshake has happened, and exactly during that clock cycle this control reset pulse is going to get set to 1. But in the next cycle I will not have the do write corresponding to this, because that do write is also a one cycle thing. Once valid and ready have both agreed that the write has completed, do write will go back to 0 and wait for the next write to occur, right. So, control reset pulse will become high for exactly one clock cycle, and in the next clock cycle this control reset pulse will be sent back to 0. Okay. Now, we also have some logic corresponding to the wrap bit. If wrap pulse, where is this coming from? From my pulse width modulation core, and we will look at that in a moment. If the wrap pulse is high, then the status wrap should be set to 1. When will it be set to 0? We will see that when we look at the explicit method of clearing the status bit. And similarly, if the status wrap signal is 1 and the update pending signal is 1, it means that the update has completed and I can clear the update pending bit. Okay. So, all of these are logic that we already described. Inside the case statement, we basically have some fairly straightforward logic. It basically checks if you are writing into location 0, I need to either set the control enable and the control reset pulse as required, and of course return that the write succeeded. If it is address number 1 that corresponds to the period, I write into the period shadow register, not the active register, and then I need to check, and I can basically say if control enable was equal to 1, I set update pending equal to 1. Okay. This is a shortcut. This is a simple way of saying if control enable equals 1, set update pending equal to 1, else if control enable is 0, set update pending equal to 0. So, I do not need an explicit if statement, I can just say it should be equal to control enable. Now, why is that useful? Because as we will see later, if I do not have, if my control enable is 0, then I do not really need to bother about update pending. It means my counter is not currently active and I can straight away change the period as well as the duty cycle. Okay. But you will notice that within this always block I am only changing the value of period shadow. So, where does period active get set? We will see later, right. Similarly, address number 2 corresponds to the duty. Again I update only the shadow variable and I check whether an update should be marked as pending. And finally, I want to clear the status register, right. So, this is checking, am I writing into byte 0 of the status register, is bit number 1 of whatever I am trying to write, is that equal to 1? If so, clear the value of status wrap. So, this is what W1C, write 1 to clear, is implemented as, right. Now, after all of that, I can then go on. I also have the read part of it, where that is actually much more straightforward, right. When I am reading from address 0, I basically need to return control enable. If I am reading from address 1, I need to return the period. Of course, as I said, I return the shadow values here. I could also have chosen to return the active values, and I can also give the whether there is an update pending and whether the wrap has occurred and not yet been cleared. All of these can be sent back. And after all that, we finally say, okay, now I need to integrate this. I now have a period, the shadow values at least, and I want to be able to integrate them with my actual PWM core. So far that hasn't come into the picture. So what I do is I first create one new signal which I am going to send as the reset signal to my core. If my entire system is being reset, that is a reset, then yes, make this also low. Or if the control reset pulse is equal to 1, then tilde of control reset pulse will become equal to 0, and therefore reset and core will also become equal to 0. So in other words, from software I can set control reset pulse and use that in order to reset the PWM core. I also declare a wire which will be used for the wrap pulse, and now this is basically where the active values are being updated. How do I do that? I first check if control enable is low. It means I don't need to wait, I can immediately update the period as well as the duty cycle. On the other hand, if control enable was high, then I check, was there an update pending and have I wrapped around? If both conditions are true, I once again update the period as well as the duty cycle. So all the logic that we described in terms of how I want the system to behave has been encoded into the system, right? And finally, we come to the actual PWM core itself. I instantiate it, I connect up the clock, the reset, the enable signal, the period, the active values, right, the period and duty cycle active values. The PWM output basically is taken as an output that is sent out of the module, and wrap pulse over here is once again used for setting the status wrap signal. So as you can see, I just directly took a module that had been implemented without any knowledge of software, right, no concept of registers or AXI or any other such ideas, and what I have done is I have wrapped it inside something which can give me an AXI Lite interface. Why is that interface useful? Because all kinds of things like, setting the period, setting the duty cycle, checking whether the wraparound has occurred, controlling whether the counting is happening, doing a software reset of the core, all of that can now be controlled through software, right. So as you can see from here, we have taken a core which was designed without any background of hardware or of software, wrapped it in the AXI Lite which structure which looks very similar to what we used for the register bank, added some functionality like write one to pulse, write one to clear and so on, and we have a module that can actually get integrated into any AXI compliant bus interface. Okay. So how do we test whether our entire AXI compatible system is working properly? We are once again going to use Cocotb because this is after all an AXI based system, and the Cocotb AXI interface gives us a nice way of basically creating different kinds of test cases, right. So once again I have a function which allows me to reset, I declare the AXI Lite master, I have a function out here which allows me to read 32 bits at a time, right, and does the job of converting it to an integer and finally returning it as an integer. So it's just a sort of helper function that I have out here. And then finally I have my actual Cocotb tests. So the first test I write is I am going to set the period and duty cycle, enable it, observe that it actually sort of sets the wrap signal which is sticky, and then finally clear the wrap signal, right. So what I do is I basically first check that the value is disabled, that is the control enable should be 0, and I should be able to check that if I read back the status and check what the value is, that value is going to be 0, right. So these assert statements are the way by which we are writing our tests over here. I set the period and duty cycle to be some very small numbers, 9 and 3, that's because I don't want to sit forever waiting for the simulation to run. So I am just testing it with very small values, right. And what we are going to do is of course check that I should be able to read back and check, yeah, the period has actually got set properly, right. Then I enable, that is to say I write 1 into location number 0, then I wait until status wrap. Okay, how does that happen? I just basically say, okay, wait for a large number of clock cycles and keep reading from location number 0xc. Check whatever status you got over here and it with 0x1, right. What does that mean? It basically means look for the bottom bit, the least significant bit. If that value wrap was equal to 1, as we can see over here, then break out of this. So, I am not actually going to sit and wait for 200 clock cycles, right. In the meantime, keep waiting for rising edges of the clock cycle. After this, when I finally break out of the for loop, I should find that the wrap signal was equal to 1. Okay. And what I have done is, in this case, I have actually set up the counter to run, and then I explicitly wait for the system to actually wrap around, right. I keep on waiting for some number of clock cycles, and after that I verify that the status wrap has become equal to 1. If it's not, then it will basically say there's an error, the counter should have wrapped by now. In other words, I am waiting exactly for 1 cycle more than the clock period, than the counter period, and by then it should have wrapped around, right. Now over here you will notice that I am actually explicitly clearing, or rather stopping the counter, right. I write 0 into the enable signal, and the reason why I do that is, if I don't do that, it is possible that by the time I read back the value, I might have gone through one more wraparound, right. So, there is a potential race condition out there. It won't happen if your period is sufficiently large, because AXI is reasonably fast, it will take only a few cycles, but the point is AXI Lite is not a one cycle protocol. If I want to read from a particular location, it actually might take more than 1 clock cycle to respond, right. So, this is just to avoid any such problems, I stop the counter, and after that what I do is I clear the wrap by writing the value 1 into location number 0xc, and after that I should be able to read back from there, check the status and say that is now equal to 0, right. Over here you remember the status was equal to 1, over here the status must be equal to 0 because I have explicitly cleared it. Then I have one more test which basically says, okay, I can do the reset pulse and check whether it cleared properly, right. The entire status should be set, or rather the entire status should be at 0, but more importantly, if I read back from the reset pulse, I should find that the value that I read back from location number 0, right, here the value that I read back from location number 0, even though I have written a reset pulse into it, should not change from 0, right. It should not return a 1 at that bit essentially. And finally, I also have another condition which checks for, I actually wait, I write something while the system is counting, check that the update pending bit is high, then I wait for a wrap event, right. I keep on waiting for many clock cycles until a wrap event happens, and then finally check whether the pending flag, whether the status flag has cleared and whether the pending flag has cleared, right. Each of these I check separately and say yes, both of them have cleared, and now the system has actually got updated to the new value that I wanted, right. So, all of this are a set of checks that I thought of that could potentially maybe help to say that yeah, this seems to be working okay. But it is quite likely that if you really sit and think about it, there are more checks or more tests that you can come up with which would help you to have more confidence that the code is written properly, right. So, this is by no means supposed to be an exhaustive set of tests, it is just a set of tests that seems to sort of capture what we want. So, let us see what happens when we actually run this through with Cocotb, right. And as we did before, what we can do is we can just type make, because all the setup for Cocotb has already been done appropriately, right, and it prints out a whole lot of messages about what it has inferred regarding the system. It, for example, finds that there is an address width of 6 bits, the byte size is 8 bits, the data width is 32 bits and so on, and it does a bunch of reads, writes, etc., and then finally says all the 4 tests that we had created have passed, right. We can also open up the waveform in GTKWave and right now I am just at one shot importing all the signals, right, which is a bit messy because unfortunately what ends up happening is you see, for example, signals like W data is here, W ready is here, but then W valid is one signal away from it, right. Ideally I would have liked to group them together so that W data, W ready, W valid are all next to each other. R data, R valid and so on should be next to each other and so on, right. So some sort of organizing of the signals would have probably helped, but right now I just want to sort of show that yes, the kind of waveform that gets generated. I am not going to walk through all of this in detail. What you can see over here is that there are multiple different test cases which you can sort of make out most easily by looking at the reset signal, right, where we can see that yes, the reset is low for a little while, it then goes high. This is because every one of our test cases starts off with a reset condition, and then while the test itself is running, reset is going to be high, right. There is, you can see that the actual counter itself is counting, right. There are parts over here where the counter itself is going through a counting process. We can see that the duty cycle is being changed to different values, 3 over here, 4 over here. The period is being changed, it has an initial value of FF, it changes to 9, it is being changed to 10 at this point, right, because the different tests had different values. So each of these different things can be sort of examined and understood in the waveform if you find that there is a bug. If everything is working properly, then presumably the waveform by itself is unnecessary, although it's good practice to make sure that you understand what is happening at different parts of the waveform.